afternoon, everybody. Let's get started with our session on recursion. If you have not seen me before in my sorting and other videos, I am Ashokan. I've been training for the last 30 years. I'm very interested in certain aspects of programming, functional programming. My favorite language is Python. You might also have seen me in the Python videos. Now, recursion often makes people feel a little defensive. Many students of computer science feel that they don't understand recursion. It's something very complex. Well, I'm not going to tell you it is easy or it is trivial. Not at all. But with a little effort, you can understand what recursion is, how to read code, recursive code that is, as well as how to write your own recursive code. It's fairly simple once we get the hang of it. Sometimes we get a little lost in the details, or sometimes we don't understand where it is going. Suddenly we have one aha moment. This is what recursion is. Okay. I'm hoping for many of you, at the end of today's session, you will be able to say, now I understand recursion. I would love to, of course, hear from you while we are talking, as well as later if you have any questions. Let me get back to my presentation and let's get started. What you see on the screen is a famous drawing by one of the most wonderful artists by name M.C. Escher. It's called Drawing Hands. As you can see, one hand is drawing the other hand, which is drawing the original hand. Pretty wonderful when someone can have such an imagination and draw. Okay, well, Ashokan, do we need such imagination and drawing skills to understand recursion? No, not at all. It's simply a wonderful piece of art which I wanted to show you to appreciate. If you're able to see this and say, wow, it's wonderful, it looks great, that's all I am asking you to do. You will be able to appreciate and understand recursion too. Let's start with a formal definition of what is this recursion. It's simply a way of solving problems. Essentially, a method of solving computer programming problems. The interesting part where recursion gets in is the solution depends on the solution to a smaller version of the same problem. You have one problem to solve, you come back and reduce the problem to the same problem of a smaller size, and then say the solution to the original problem is this plus or this plus this smaller problem solution. Let's repeat that. In recursion, you start with a problem and then you say the solution to this problem is something plus the solution to this smaller problem, which is actually the same problem of a smaller size. That sounds very complicated. Yeah. Let's look at an example. What example? How do you sum all the elements in an array? Sir, you write a for loop. Yeah, of course. That's one way of doing it. You can write for I equal to 1 to n, I equal to 0, I less than n, where n is the number of elements in the array. Then put one variable called total and then add each element to the total. That's definitely one way. That's probably the easiest way also. But you may be surprised to know recursively we can solve the same problem. Sir, why are we doing this recursively when the for loop is something we already know? The reason I am talking about this is for you to appreciate recursion is not that complex. It occurs in every context. Certain cases recursion is a very good way to do. Certain cases it is okay, certain cases it is not. But there is nothing magical about recursion. That is what I am trying to show you by this example. We define the sum of an array A, capital A. What is it? We will say, take the first element, we will call this A0. Now the sum of the whole array is A0 plus sum of the remaining array. Very straightforward. I have used slightly mathematical looking notation. A prime stands for, as you can see on the slide, A1 to AN. The original array was A0 to AN. So what are we saying? The sum of an array is the first element plus sum of the remaining elements in the array. But we can apply the same principles to this new sum of A prime. A prime is what? It is another array. Where does it start? In A1. So the sum of A prime is A1 plus sum of A double prime. What is A1? The first element of A prime. What is A double prime? All the second element of A, so on. Now look at it. So sum of A is A0 plus sum of A prime, which is A0 plus A1 plus sum of A double prime, which is A0 plus A1 plus A2 plus sum of A triple prime, and so on. When do we stop? That's a question you have to answer. So all this is nice, but when do we stop? We stop when this A array is no longer an array, only one element is left. That's all. So this is how we can use recursion, understand recursion even in the context of a simple summing of an array problem. Now let us look at another problem for which we can do a recursive definition. We say n is a power of 2. What does it mean? It must be even. Okay, if n is even, what does it mean? It is divisible by 2. So what happens next? If it is divisible by 2 and whatever you divide is also a power of 2, then the original is a power of 2. That's what we have written there. N is a power of 2 if and only if n is even and n by 2 is a power of 2. Now you remember our original definition, we said recursion is where we say a solution depends on the solution to a smaller version of the same problem. What is the problem here? To determine whether n is a power of 2. We are saying n is a power of 2 under two conditions. One, n must be even n must be even and, not or, and n by 2 must be a power of 2 in itself. That sounds very simple. So n by 2 is a smaller version of the same problem we talked about. Why do we call it smaller? This is where most of the people have a difficulty in understanding recursion. They cannot visualize when it stops. So let us see whether we can write. Sir, how do we understand recursion? The idea is often to say, use a paper and pen and try to write down whatever you are going through step by step. Let us try and understand this once again. What is the point we are saying? N is a power of 2 if n is even and n by 2 is a power of 2. Let's start with a number. Say 28. Is 28 a power of 2? Our method says, is 28 even? Yes, n is even. And then if 14 is a power of 2, 28 is a power of 2. Sir, where is recursion now? Please remember, for 14 we apply the same method. So when is 14 is a power of 2? If 14 is even and 14 by 2 is a power of 2. Is 7 a power of 2? We don't know, but we continue with the same approach. Is 7 even? No. So obviously 7 is not a power of 2. So 14 is not a power of 2. So 28 is not a power of 2. Simple. Let's see how it works for an actual power of 2. Let's choose 16. Is 16 a power of 2? Let's rewrite. If it is even and n by 2 is also a power of 2. So for 16, n is even, so n by 2 is 8. We try. Is 8? Yes, it is even. N by 2 is 4. 4, it's even. Yes, it is even. So n by 2 is it a power of 2? 2, okay, 1. 1 is not even. Oh, what do we do? Okay, we forgot to actually take care of the exception statement. Some of you might actually have noted what I did in the slide. So let's go back to the slide for a moment. It's written all over the place, so let me clear this first. It's okay, we can read it. We are saying at the bottom, of course it is an exception if, as you can see, we have written here n is a power of 2 if and only if n is even and n by 2 is a power of 2. Of course 1 is an exception since anything to the power 0 is 1. Oh, so that is what will save us. Let us start again with 16. We will write here itself and see how it goes. What are we going to check? We are going to check whether n by 2 is n is even, sorry, not n by 2. Whether n is even and then whether n by 2 is a power of 2. That is it. We start with 16, n is even, so n by 2 is 8. So now we say if 8 is a power of 2, 16 is a power of 2. Okay, we got 4, we got 2. Sir, 2 is a power of 2, you already know. Yeah, we can stop there also, or you can say 1 is a power of everything, so we stop with 1. So this is the idea of a recursive algorithm. We must have a particular case for which we no longer will apply recursion, but will stop and say we know the answer. That is critical for a recursive algorithm to work. So let's summarize. We start with a problem, we divide it into smaller version of the same problem, and we have some special case or an end case for which we know the answer to the original problem. How does that apply to this? Is even, is power of 2, sorry. We know that for the case of 1, is power of 2 is true. In all other cases, we first check whether it is even. If it is not even, obviously it's not a power of 2, because we have already verified whether n is 1. If it is an odd number other than 1, it cannot be a power of 2. Okay. If it is an even number, what happens? Now we get the smaller version of the same problem. That is, if n by 2 is a power of 2, so is n. So this algorithm simply says, have you got 1 in your hand? If so, you are done. The answer is, you started with a power of 2. Okay, you don't have 1 in your hand. Do you have an odd number? If so, it is not a power of 2. We are done. What is remaining? We don't have 1, we don't have an odd number, so we have an even number. For even number, what does our algorithm say? It is a power of 2 if and only if n by 2 is a power of 2. So divide that number by 2 and then repeat the same process. That is a classic simple case of recursion. Now let us see the next. The next example is a non-numeric example. What is this, sir? You are taking always power of 2 and some number and all that. Yeah. So we will take a string. We are saying a string is a palindrome. When is a string a palindrome? If the first character is equal to the last character, then it can be a palindrome. If the first character is not equal to the last character, it is not a palindrome. Oh, by the way, I hope you all know what a palindrome is. If not, here is a quick definition. A palindrome is a word in English which reads the same way from the beginning to end. Like what? The most famous example given is madam. It reads the same way from this way, it reads as madam. This way also it reads as madam. Here another example, Malayalam and so on. You can check the net for more interesting examples, phrases as opposed to palindromic words and so on. Now let's get back to our definition of a palindrome. We said a string is a palindrome if the first character is equal to the last character, and what remains? Whatever is in the middle is also a palindrome. This is where the recursive definition is coming. We are saying if the first character is not equal to the last character, it's not a palindrome. Okay, if the first character is equal to the palindrome, now we have a smaller problem. What is the smaller problem? Take a new string which is the second character to the penultimate character. If that is a palindrome, the original was a palindrome because the first and last were equal. What is in the middle? If it is a palindrome, the original is a palindrome. So a recursion can also be used for checking for palindromes. We are not going to do this. In some languages it is not easy to do this, but in other languages this code is a lot easier to write than other code. So depending on that depending on the language of choice, we can do different things. Okay, so where are we next? Actually, let us write the code for the power of 2. Let me switch to writing code instead of talking about the problem. Here we have the e power of 2 function in C99 and C11, which is the latest standard for the C language. Boolean is a data type, but in order to use it, you must include the stdbool.h header. So I have added this. It is simply defining one function called e power of 2. That function takes one integer argument. As you can see, the function's name is e power of 2. It takes one integer argument. It returns a boolean. If you just now discussed the algorithm, so let's go back to it. If the number is 1, it is a power of 2 because anything power 0 is 1. So that is what this part is doing. We understand that part now. So then we check whether it is an odd number. Why do we check whether it's an odd number? Because we know if it is not an odd number, if it is an odd number, it's not a power of 2. So that is what this part is doing. So we understand this also. First part, we check whether n is 1, in which case we say job is over. The number is a power of 2. If now it is an odd number, what do we say? It's not a power of 2. Because it's not 1, and 1 is the only odd number which is a power of 2. We have an odd number on hand, so we simply return false. Which means if control comes here, what do we know? We know that n is not 1. We also know n is not odd. In other words, we know n is even. But our original definition nicely said a number is a palindrome if a number is a power of 2 if it is even and n by 2 is also a power of 2. So we simply make a call to the same function e power of 2 with n by 2, which is the critical point of recursion. If you notice, we started defining a function called e power of 2. It took an argument n. Then we checked whether there were the terminating cases are true. In two cases, our algorithm will terminate. It will terminate if n is 1 or if n is odd and not 1. In both cases, we know the answer. If both cases don't apply, the recursive case applies. What do we say? We have a number which is even, so divided by 2, whatever that number is, that is the original number's fate. If the number divided by 2 is a palindrome, is a power of 2, so is the original. If the number divided by 2 is not a power of 2, so is the original. Let's check at it once again. We start by, forget the definitions and bools and header files. We start by checking whether we have a special case which gives us true a special case which gives a case which gives us false, then we have the recursive case, which is almost always a standard structure of any recursive routine. There is one terminating case with which we start our whole thing, then we have a different case, and then we can finally call the recursive case. What do we call it recursive? We are returning the result of invoking the same function which we are defining. That is why this is a recursive function. But remember, we said in recursion, the answer depends on the smaller version of the same problem. We started with n, we are now with n by 2, so it fits the textbook case of recursion. E's power of 2n is dependent on E's power of 2 n by 2. So that's how we should be able to read this code and understand it. Because there is normally a structure to recursive code, it will often have some special cases which are terminating the computation, and it will be followed by a recursive case. In the recursive case, it will be a smaller problem. In the case of numbers, it is obvious what the smaller problem is. The smaller problem is n by 2. Let's see another problem which we haven't discussed so far. This is the greatest common denominator, or as it is known in some parts of South, the HCF, highest common factor. What is the highest common factor of two numbers? Find all the factors of the first number, find all the factors of the second number, and then pick the largest. You can do that, or we can do recursively. If one number divides the other number, obviously that number is a largest factor. What are we saying? If you have two numbers A and B, if B divides A, B has to be the largest factor for A and B. So answer is B. If not, the algorithm says what you are looking for is the GCD of B and the remainder when A is divided by B. Sir, how will this work? Let us try two numbers, 52 and 65. What is the GCD? Looking at it, we can see 4 into 13 is 52, 5 into 13 is 65, so the common factor is 13, and that also is the highest factor. We can do that, or we can do as per our algorithm. What is our algorithm saying? First look at A percentage B. Sir, A percentage means A must be bigger than B. Actually, we can avoid that problem also the way this code is written. To show that, let us see. 52 modulo 65 is actually 52. So what will happen? If I give this as A and this as B, then the next invocation will be GCD of B, comma A percentage B. Since B is, this would give you GCD of 65, comma 52, which will give me GCD of A percentage B is not 0, so then 52, comma, when you divide 65 by 52, the remainder is 13. So now we have A percentage B true case, so the answer will return 13. Let's try again with another two set of numbers. 70 and 28. As you can see, the common factor is 14 because 5 into 14 is 70, 2 into 14 is 28. So what do we do? A percentage B is what? A is not dividing, so 70 percentage 28 is 2 into 28 is 56, 56 minus 70 minus 56 is 14, so I have 14. So this is A, this is B, and this is A percentage B. So my answer would be GCD of B comma A percentage B. So starting with GCD of 70 comma 28, I ended up with GCD of 28, 14. Now code says if A percentage B equal to 0, 28 percentage 14 is 0, return B. So the answer is 14. We found out in one shot. So this is another simple recursive code. Let's once again understand where the recursion is coming from. You can see we are calling GCD with 2 arguments, and we are making a recursive call to GCD with 2 smaller arguments. How do you know it is smaller? See, A percentage B is going to be smaller than A and B. So automatically we are reducing one argument at a time, so it will go on reducing. So what is the case, terminating case? When, sir, what happens if there is no GCD, there is no factor common? Then mathematically 1 will be common. So these two, when B becomes 1, we will return 1. Let's see the answer, sir. Okay, let us look at 13 and 6. So A percentage B not 0. So I have to try GCD of 6. And what is the remainder? When 13 is divided by 6, 1. So A percentage B equal to 0 is true. So 1 will get returned. So this algorithm works for when the numbers are relatively prime, have no common factors in all cases. This is actually known as Euclid's algorithm, named after the great mathematician of ancient Greece, Euclid, who gave us geometry. So, as you can appreciate, the 2 circle parts tell you that we have a recursive call, and the fact the number is A percentage B, one of them is getting smaller, tells you we are in line with our original definition of a recursive. Recursion is when you have the answer depends on the smaller version of the same problem. Alright. Some operations are recursive by definition. In fact, very often colleges would have taught you recursion by using these examples. So let us see that so that we are able to relate to that. What are we saying? Factorial of 1 is 1. This is the terminating case for recursion. For numbers greater than 1, factorial of n is n into factorial of n minus 1. This is the definition of factorial n. Now this is what we call a recursive definition. Sir, what is a recursive definition? The definition of fact contains fact. So fact is defined in terms of itself. So it is a recursive definition. Sir, but how do we use this to calculate? Like we said earlier, there must be one terminating case, which we have, factor 1 equal to 1, and there must be a lesser problem, and that is here n minus 1. So we can expand this to, for fact n minus 1, this is what is fact n minus 1 is n minus 1 into n minus 1 minus 1, which is n minus 2. So we can easily go on till we get 1, at which case we can stop and say what we want is n into n minus 1 into n minus 2 and so on up to 1. So this is a recursive definition of a factorial. Now we can, if you want, fairly easily write the code. I'll write it now straight away. What do? We are writing in C, so we'll say int fact int n. I'm just using the name. So if, write the terminating case first, n equal to 1, return 1. That is all. Otherwise, return n into f of n minus 1. This is the exact translation of the code of the procedure we right now have here. As you can see, factorial n equal to 1, so we are saying if n equal to 1, return 1. Factorial n is n into factorial n minus 1, so return n into f of n minus 1. So here is the recursive call we have done, and instead of n we have done by n minus 1, so it is a lesser problem, and there is a special case, terminating case. So our code contains all the right things. Pretty good. Let's move on to the, I promise you, the last recursive definition, which is slightly more complex than the previous one because of the what is called a two-term recurrence. Let's look at it. We are defining the Fibonacci series, the well-known Fibonacci series. What are we saying? Fibonacci of 1 is 0, Fibonacci of 2 is 1, Fibonacci of n is Fibonacci of n minus 1 plus n minus 2. That is, the first term is 0, the second term is 1. After that, each term is the sum of the two previous terms. Let's look at it. The first term is 0. Okay, we understand that. The second term is 1. We understand that. We need to specialize into two terms because we are defining from the third term onwards. Each term is the sum of two previous terms. So we need two separate definitions for this recursive definition to work. Probably you have seen this before. Let's write the Fibonacci code again. It's fairly straightforward again to write. What will we say? If that is all. So automatically we will get the same result as before. I suggest you implement the last two, Factorial and Fibonacci, yourself, writing recursive code and check for yourself. Let's summarize. Recursion occurs in three contexts. Like we saw, the first context was the is power of 2 algorithm, where we specifically did it inductively. What do you mean by that? For n, n plus 1, n plus 2 and so on, we could define it, and from that we could derive a recursive way of doing this. Or the computation itself is defined recursively. Example, the factorial. We said factorial of 1 is 1, factorial of any number larger than 1 is n into factorial of one number less than that. One thing which we did not touch on, but which I want you to be aware of, is certain data structures are recursive by definition. For example, a tree, a binary tree can be thought of as a right tree plus a left tree. So a tree is defined in terms of itself. We don't have time today to go into the details of such data structures, but maybe at a future live session we will talk about recursive data structures and how to write code about it. Let's close. Before that, let's define the recursion once again, and then we'll close for the day. Recursion is a way of solving a problem, a computer program. And what is most important about it is, it solves it by constructing the solution to a smaller version of the same problem. That is what is most critical about it. So, we use recursion when we can reduce the size of the problem and solve the problem that way. Let's recap. The recursion's definition is, the solution to a problem depends on the solution to the smaller version of the same problem. So GCD of two numbers is dependent on GCD of the smaller number and the remainder when the larger number is divided by the smaller number. This is obviously a smaller version of the same problem, and it stops when the smaller number is 1. A factorial is similarly defined, and factorial of n is n into factorial of n minus 1. So n minus 1 is smaller than n. So this stops. The terminating case is when n equal to 1, for which we know the answer. That is the critical point of a recursive computation. We need a terminating case which we check first in the code. If you remember, in e's power of 2 we did the same thing. If n equal to 1, return true. If n is odd, return false. Otherwise return e's power of 2 n by 2 itself. So this program, if you study in leisure, you will understand the complete structure of how to write recursive code. Identify the terminating true case, identify the terminating false case, then recurse. I hope you enjoyed this lecture as well as you understood about recursion. If you have any questions, you know where to ask them. Thanks for listening into my lecture, and thanks for being part of Talent Sprint's lecture series. Have a great weekend. Bye.
Sorting algorithms are a very important subject matter of study. I am going to discuss some of the well-known sorting algorithms, but we are not going to be writing code, but instead we are going to be using one of the oldest known pastimes, playing cards. We will use playing cards to understand sorting algorithms. Like sorting, searching is also very important. So people often find it difficult to understand. We have got a very easy way using cards again for you to understand searching easily. I have cards numbered from 10